Okay, first I'm going to take this system and I'm going to apply a force slowly to this system. Now what I'm expecting will happen is that because this string is going to have the weight of the mass plus the amount of tension that I'm applying being supplied to it, that should break first because this just has the tension I'm supplying to it without the weight. Let's see if that happens. Pulling it slowly, and yes, it broke, the upper string broke first. But now, because of inertia, if I apply this force fast enough, I'm going to take advantage of the fact that inertia is going to prevent the force that I'm applying from affecting the upper string before the lower string reaches its breaking point. Okay, here we go. You see, the string did break on the bottom side. It just flew out of the little lasso noose that it was in, but it broke first down below because the inertia of this thing prevented the tension from reaching the upper chord until the bottom chord had reached its breaking string. Okay, and so that's the way that it should be looking after the bottom side broke first. Okay, so this, of course, is a very kind of old demo that has been used many times in the past, but it's basically the same idea as what we just did. Because when we pull this slowly, we see that the static friction force doesn't have to exert much force, and we're nowhere near the maximum static friction necessary to keep the mass securely attached to the newspaper. But when I pull faster, the inertia of the mass causes it to resist the acceleration, and that increases the force of friction until we exceed the force of static friction, and voila, it is gone.
We have another inertia demo here, and the question is, here we have a plastic straw and a potato, and can we slice this straw right through the potato? Well, the idea is if we're doing this slowly, this is not going through the potato, okay? However, if we move this very quickly, we could get it right through the potato. And we're moving it fast enough so there's no resistance to the force of the straw piercing the potato. So yes, the straw can be mightier than the potato. We are ready, Dr. Seth.
I know how to do magic.
I think you know how to do science.
Try this
That
one.
was inertia.
Try this one out. This is so fun.
Can Dr. Seth get the nut in the bottle by using the power of inertia? Yay! Good job, Dr. Seth! He got it! And he made sure he didn't apply any horizontal forces. So what do we have here, Seth, instead of a penny?
An eraser.
And is an eraser stickier than a penny?
Always.
Is it? Okay, great. So let's see how well we can do our inertia at work here. Ah! It sticks to the paper. Looks like it is going to have the same motion as the index card. It won't just have gravity.
But if you put a penny under it, then...
What happens if you put a penny under it? Hello there, students. Some simple demos on Newton's second law. Force is proportional to the acceleration of an object. The net force is proportional to the acceleration of the object. That's a better way of saying it because what we want to do to understand the motion of a body, and we're looking at one body at a time, we want to look at all the forces acting on that body, add them vectorially, and see if there's a net force. If there's a net force, then there's acceleration that's non-zero. If the net force is 0, then the acceleration is 0, and we call that equilibrium. That means the body is not accelerating, so it's either moving with constant velocity or is at rest. So here we have a cart, and the body, this cart, if you hold it still for a second, is, that will put a block up. So we see that this body's at rest. That means the net force value is 0. So for our purposes, we'll look at all the horizontal forces and all the vertical forces. So the vertical forces acting on this body are gravity. Okay, so the weight force is another way of saying that. So the mass of this cart times little g is the weight. And then there's the upward force, the normal force, which is a subset of the electromagnetic force and is acting upwards to counteract the weight of this body, so the weight force. So these two forces sum to 0 because you don't see any acceleration in this direction. Okay, and what we know is that if we apply a net force, so if I go ahead and push the cart, it begins to accelerate. So there's a net force along this horizontal axis, and the acceleration is in the direction of that net force. Okay, one more time. So F equals ma, or F net equals ma in that case. So there is a little bit of air resistance or friction acting in that direction, but the net force, in this case, the friction is a little more complex because it's got wheels on it. Something to talk about. But if I push it this way, there is a net force in that direction. Okay, so looking at Newton's second law and the special case of equilibrium. Here we have a DIY, do-it-yourself equilibrium project, as outlined in the lab, okay, which you could put together yourself. And here we look at a system that's in equilibrium, analyze all the forces in this system, and we could find what's called the unknown tension in the string. So tension is a force that acts along a string or cord. And so what we have here is we have a box of Jell-O that has mass. So of course it has gravity acting on it and pulling it down towards the center of the earth. So if it has mass, it has weight, and we find the weight, which is equal to mg, and that's the mass is 85 grams here times the acceleration due to gravity. Of course you have to convert your units. So we have weight acting down, tension, this string right here is tension acting upward. So when we add those two vertical y forces, vectorially, they sum to 0. So the net force is 0, which is equal to ma. So we have force, the net force is 0, so acceleration is 0. Okay, because they're proportional. Okay, now what we have here, since we have this tension force right here, we notice that it's connected to these other two strings. So we can use this point of connection to equate this tension force to these other two tension forces. Okay, so we call this T1, tension 1, tension 2, and tension 3. We could use what we know from this third tension force, and it's equating to the weight force and using Newton's second law to figure out these other two. So what we would have to do for these tensions, since they're at angles, is we'd have to measure the angles from which they hang at. So we use a protractor for that. Okay, we measure this angle here, theta 1, and we measure this angle here, theta 2, and that will give us the x and the y components of these two tension forces, because they have a little bit of horizontal force and a little bit of vertical force. Okay, so what happens is we have this third tension downward. So this third tension is all vertical, and it's going to be counteracted by the vertical tension of this first string here, of this T1. So T1y plus T2y, this vertical component of force, those two summed together will be equal in opposite direction to this third tension pointing down. Okay, so that gives us an equation. That's the handiness of Newton's second law. And then we also have this horizontal component of tension will be equal and opposite to this other horizontal component of tension. And that gives us another equation. So those two will sum to 0 because there's no acceleration horizontally. So their net sum is 0 for the force, which is equal to mass times acceleration. So we can use this system in equilibrium to find these unknown tension values. And further, if you wanted to verify the mass of this, you could use a handy weight scale like this, which will measure out the 85 grams. Okay. So this gives me my 85 grams. And then it comes close to about 0.9 newtons, between 0.8 and 0.9 newtons as far as the force goes. Okay, so I can verify my mass value, and which will allow me to have my weight value. All right, so systems in equilibrium are very handy to apply Newton's second law to and find unknown values. Okay, another demonstration we're going to do here is we're going to look at adding an angle to an incline. We're going to do a mass on an incline and analyze the forces there. So here I have a block of wood of unknown mass. Okay. So typically we have in our physics problems, we know what the mass is, but here we're just going to do a demo. And what I'm going to do is first look at a flat surface. So I just have a horizontal surface and want to analyze the forces acting on this mass. So what I have is weight force acting down, vertically down. So I have the weight force acting downwards towards the center of the earth. And then I have the normal force counteracting that weight force, that vertical weight force going upwards, perpendicular to the surface of this object. And that normal force is created from the compression of all the atoms in there. So they're pushing back up as the mass, the gravity is acting on the mass and pushing down into the table, or the surface rather. Okay, now the moment I start raising this and creating an angle of my incline, which would be right here, okay, and I could measure the angle using a protractor. So the moment I start raising this, I'm going to create my weight force so that it's going to act in two different directions, two different components of motion. So what happens is now I have my normal force acting perpendicular to the surface this way, but my weight is going straight down to the center. So it's going to have, I'm going to have a vertical component of weight acting down, and I'm going to create this horizontal component of weight that will eventually at a certain angle accelerate down the ramp, because it'll create a net force in that direction. Okay, so as I lift this up, okay, you notice it's not moving yet, and that's because it's stuck. There's static friction holding this up. So right now I have some weight force horizontally, but I have a static friction force. It's a contact force between surfaces. So that's holding it and opposing that weight force. Up until the point I get to a certain angle and it accelerates down the ramp. At that point, the static friction force is the kinetic friction force, and it opposes a weight force, but it's going to be a lot less, whereas the x component of weight force has a net force going down the ramp. Okay, and that's my horizontal axis. And still I would have my upward normal force counteracted by my y component of weight. Okay, so I'm going to try here. Can you repeat this? So it's really important to analyze all the forces, look at the angles, and make sure all your vectors sum up along the horizontal direction and the vertical direction. Get your equations of motions correct. So at some point, this accelerates down. Okay. So again, we have friction, kinetic friction, x component of weight, normal up, and y component of weight down. Now, to add a little bit of a challenge to this, I have dog assistant here. We're going to create a little more stickiness. So we're going to create a little more static friction between our surface of the wood and the ramp. And as you can, yes, this will create a situation where we'll need a steeper angle to accelerate the block down the ramp. So I'm going to lift, 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 lift. And you can see it's going to take a lot more angle to get that weight component of force along the horizontal axis to get it to overcome the static friction force and have a net force equivalent to the mass acceleration in that direction. Here we go. Voila, there we go. So it eventually does accelerate, but it takes a steeper angle. There's a lot more friction involved. But once it gets moving, it's all, we have kinetic friction, not enough to oppose the horizontal component of weight. So this is a good experiment to do for different surfaces. And if you know the mass of the block, you could find some unknowns like your friction force and do the computations.
All right, for every action, there's an equal and opposite reaction.
So students, we are going to explore some of the concepts in our fourth lab today, which is about forces. We're doing an introduction to the different types of forces there and exploring them in a little bit more in an experimental context and exploring the force laws in a little bit in depth. Those are these 3 laws of motion which dictate how forces change the motion of an object and allow us to do a lot of problem solving. We'll see that Newton's second law is profound in being able to solve for a lot of unknowns. So we're going to have 2 parts. Part 1 is different simulations we're going to do. And when we look at part 1, the first part is inertia simulations. Okay, and there's a lot of really great little experiments you could do for inertia. We'll show some of those in some video clips. The simulation we're talking about is if you have a bus. So if you have a bus or some other vehicles driving along, okay, and all of a sudden it comes to a sudden stop, what's going to happen to the motion of the objects inside? So if you had a bowling ball, or in this case we have a driver that's on a wheeled chair that can move back and forth. So if this comes to a stop, what's going to happen is the person or the bowling ball on freely sliding surface will go forward, will continue going forward until they reach the bus walls, which will tell that object to also stop. So it takes a while to communicate that force to the rest of the objects. So we know by the laws of inertia, if an object is in motion, it will continue with that motion unless a force acts on it and changes that. So if I take a ball like this, and if I were to throw it outwards out into space and there were no forces like air resistance acting on it or gravity, it would continue with that same velocity indefinitely. So objects continue with that same velocity state, whether that be at rest or in whatever velocity they have. It will take some net force to change that velocity. So the question is, it stops, or it's at stop and it starts again. What happens to the motion of the objects inside? Okay, so if you look at the velocity vectors of the bus will have, if it stops all of a sudden, okay, in this case actually I should say the acceleration vectors. So if it stops, what's going to happen is we'll feel that acceleration this way, but the ball will continue to move that way. Okay. That will be the ball, and that would be the bus. And we also have other objects like a helium balloon. So you want to think about what's going on with that one, how the force is communicated to the balloon, and the pendulum. Okay, so inertia is the first law that we explore in the simulation. So the next is exploring the second law, which is the one we use the most when it comes to problem solving. The second law is nothing but the sum of all your forces is equal to ma, or in other words, force. That force is proportional to the acceleration of the object. And to apply this law, you apply to one body at a time. So the way they're proportional is to a constant, which is the mass, right? So if I were to plot my force versus acceleration, here's my force along the vertical axis, acceleration along the horizontal axis, and I collect my data, I would find that the slope would equal my mass. And, okay? So lots of problem solving. So this lets us look at all the forces horizontally to understand the acceleration of the body in the horizontal direction. Look at all the forces vertically to explore the acceleration of the object in the vertical direction. And of course, you can extend that to 3 dimensions as well. Okay, so what we know is that if there's a net force, if the net force is equal to 0, we say there's no acceleration. And we have what we call equilibrium, which can occur if you have constant velocity or object at rest. Those are equilibrium conditions. When the object's at rest, we say static equilibrium. And then when the net force is not equal to 0, okay, which is equal to ma, there's acceleration. And to tackle these problems, when we do look at the second law of Newton's, when we look at the second law, what we do is problem solving. We do a free body diagram, which I call FBD for short, and equations of motion. And the equations of motion are always your sum of all your x forces along the x direction. Would be, you want to identify all the horizontal forces acting on an object, and then you likewise want to identify all the vertical objects, all the vertical forces acting on the object, to understand the motion of the object in the vertical direction. Okay, next up we have our next simulation, which entails third law. And if I apply a force on the object, that object will apply a force equal and opposite magnitude. Equal in magnitude back, opposite direction. Another way of stating the third law is F of object 1 on 2 will be the negative of F2 back on 1, object 2 back on 1. So, or we could say F1 on 2 is equal to F2 on 1. And the simulation deals with, okay, if I have 2 blocks and I apply a force this way, which is an applied force for some force that is just a generic force, like if you're pushing on the object, we'll call that an applied force. Sometimes we call that, we say applied force is thrust or some other unknown force that we don't know the value of or the computation for. So if I apply a force on this block 1, okay, it's going to communicate that force onto block 2. Okay, so force of block 1 will be applied to block 2, and block 2 will apply an equal and opposite force back on 1. So I'd call this F1 on 2, and then I'll have a force back, which would be equal in magnitude, opposite direction, which would be F2 on 1. And to identify the motion of the object, I do a free body diagram for 1. and then I do a free body diagram for 2 separately to analyze the motion each individually and understand each individual acceleration. And I can use that once I identify all the forces in 1, identify all the forces in 2. I can look at the equations of motion and solve the problem at hand. Okay, so that's how the third law works. For every action, there's an equal and opposite reaction, is another way of saying it. So, of course, if I apply a force on this ball, it will apply a force back on the other one. So that's the way the third law operates. Lots of really good demos on that one, and we'll show those in our video clips. And then the 2 other simulations that are left are about applying Newton's second law, which we'll go into more in our next lab as well. Okay, there are lots of problem solving associated with the second law. So what we have on the fourth simulation is then we have a box on the incline. And the idea is a box or an object. It's here we have an angle. Okay. And let's say it's initially at rest. What we want to explore is what is the angle to start the motion. / get it to accelerate downward. Okay? So the idea is if I lift this, and I'll do this with a ramp, I could do this at home. If I lift this, at what point will gravity have a net force on this object so that it accelerates down the incline? Okay, now the key here is doing a free body diagram. So you'll find the angle on your simulation, but to understand how that works into the problem solving is to understand all the forces on this object on the incline. So if we look at a free body diagram of this, blue's not working, we would have our weight force, weight or Fg, which is mg of the box, the mass times the acceleration due to gravity. Okay, that's one force we identified. Then we'll have the normal force, which is a subset of one of your fundamental forces, the electromagnetic force. It's a contact force, and it comes from the contact of 2 objects together. So there's a lot, you can think of all the molecules in the object as little springs. So when you push on the object, it's pushing back on it through the atoms. This is your normal force, so Fn or N are the typical notations. And the other thing is there's a contact force called friction, which slows the object, will make an object be stuck. That's your static friction, or kinetic friction, which is the opposing the motion the object would go in. So in this case, the kinetic friction will act opposite to the object and go this way. Okay, and that's F or capital F sub F. Okay, so what's going to happen here is the moment the angle is sufficient, you're going to have acceleration downward. And the acceleration comes from looking at the components of your weight force. So the weight comes down this way, and the normal force goes upward. So what we do to problem solve when we have inclines and angles involved, and want to break it down into the 2 components of motion, which is your x components and your y components, is we align our axis so that along the x-axis we have friction and the x component of the weight force, and along our vertical axis we have our normal force and our y component of our weight force. Okay? So if we look at this, we break down the motion, we would see we have a x component of weight and a downward component of weight. Okay. So the moment that this weight force is larger than the friction force, it's going to slide down. So, and that's going to be related to that angle. So what you have is a little bit of right angle trig here. So there's two ways of writing your weight force. So your weight horizontal force component will be the weight times, so if we look at this, this is Wx, this is Wy. Okay. Make it a little clearer there. And this right here is the same angle of our incline. Okay, so Wx is actually going to be W sine theta, or we could say it's W cosine 90 degrees minus theta. It's just easier to do your triangle geometry so that you're using your alternated interior angles to identify this as being your angle, the same as the angle of your ramp. And in that case, then you apply your laws for trig. Like this is the opposite side over your hypotenuse. Okay? And so either one of these will be sufficient to use for your x component of weight, and your y component of weight will be W. In this case, Wy will be cosine. It's adjacent to the angle, cosine theta. Or you could say W sine 90 minus theta. Okay. So what we have here is you want to first look at the free body diagram to analyze the problem. And then second, I already started that, is once you have these three main forces identified on that body, your second job is to write the equations of motion, which comes from Newton's second law. So we look at the x, so we know the sum of all our horizontal forces is equal to mass times acceleration in the horizontal direction. And the moment this box begins to slide down the incline, that is non-zero. It's not an equilibrium problem. So what happens next is we say that what composes of these forces, and I'm going to say positive is to the right and positive is upward in my convention for my vectors in our diagram. What I'm going to say is that friction minus the weight. Okay, so I'm going to have, I think my arrow for friction a little smaller. So here I'm going to have my friction force minus my x component of weight is equal to m(ax), acceleration in the x direction. Okay. And my friction force, friction is proportional to the normal force. So here in this case, we're looking at kinetic friction. So identify the type. So once it gets moving, it's kinetic friction. Static friction acts up until the moment it slips and begins motion. So now I would say the coefficient of kinetic friction times the normal force minus my x component of weight, which is W sine theta, is equal to mass of the object times the acceleration. And I'd say UK times n, my normal force, minus mg sine theta, whatever the angle is where it starts to slip, equals the mass times the acceleration down the incline, and that should give you a negative. Okay, so here I have one equation of motion that describes the motion of the object along the x-axis. The other equation of motion is along the vertical axis. Here is the sum of my y forces is equal to the net y force, is another way of saying this, is equal to the mass acceleration in the y direction. And you're going to notice there's no motion going up and down vertically on the incline. So in this case, this is equal to 0. And what we have here is the normal force minus the y component of my weight force is equal to 0. So here I have my normal force is equal to my y component weight force, which is mg. And in this case, we said cosine theta. I'm going to use that derivation since it's a little easier. Okay, that's what my normal force is. Now, if I wanted to solve for, let's say, my coefficient of friction, I would just substitute that into here if I knew my mass, and let's say I knew my acceleration value. If I knew my coefficient of kinetic friction, but I didn't know my acceleration, I would go ahead and plug those in and solve for those. Okay, so those are your two components of motion, and that's how you do a typical problem. So one of these is really important to master, because then when you start mixing in more than one object, then you're going to be doing a lot of substitutions with a lot of your equations of motion. So most important is first getting your free body diagram together, then your equations of motion with the correct sign. Notice that I'm using the sign conventions in my equations here. Okay, my acceleration here should be negative right here as well. So I should actually have a negative value in my equation because it's accelerating in the negative x direction. Okay, something to note. Be careful with those things. So the very last part of a simulation deals with drag, the drag force, which occurs when you have a fluid. We're very familiar with a subset of the drag force called air resistance. Okay? So, the drag force. Okay? Air resistance is one of these. And we're going to look at the special case of terminal velocity. And what we know is that when objects fall, right, you have a falling object, a free body diagram, which shows just the weight on the object, and the opposing force. If it is dropped in air, you'll have a little bit of air resistance. You'd have F air, or rather drag force. Okay? Now at terminal velocity, like a parachutist, what's going to happen is you're going to have equilibrium. And at equilibrium, all of a sudden, whatever that object is, let's say a skydiver, the weight of that skydiver will be countered, so it's going to have an equal and opposite vector, will be countered by the drag force. Okay? So what happens here is we have, by the second law, we have a net force downward. Okay, so that means there's acceleration that's down. Okay, here you can see that the net force is equal to 0. These are equal and opposite, and they cancel each other out. And that's what we mean by terminal velocity. So the parachutist will be traveling at constant velocity. So we can use that condition to make it, to solve the equation. At terminal velocity, we have the sum of all our y forces, which is equal to the mass times the acceleration in the y direction, equal to 0 because it's equilibrium. Okay? And what happens now is you'll say that the drag force, F drag, minus the weight of the parachutist will equal 0. So F drag will equal mg. Okay? Now, what does F drag equal to? That's the big question. F drag? Well, F drag depends upon your speed, your area, and the drag coefficient. So, to give you the equation to use, and you could look this one up, F drag is equal to 1/2 the drag coefficient, the density of the fluid you're traveling in this case the density of air, the area of the object becoming in contact with the air, times the velocity squared. Okay? This is your equation for drag you're going to use, and you're going to explore in the simulation. Now So this is the area of the body. This is your drag coefficient, which I've given to you in the pre-lab for a parachutist. If you're a parachutist, and you could think of a parachutist as a cylinder and you're falling through the air, then your C value is a cross section of a cylinder, so it's about 1.14 the side of a cylinder. Okay? And this is your density value of your fluid, and you can look up the density of air. Okay? In this case, it'll be air. Okay, so how much mass per kilogram you're packing there. So density is how much mass per unit volume you have. Okay. So that tells you how much, when you look at the density of the air, which of course is thinner the higher up you go, so that's going to change as well. You can see how drag can be rather complicated to compute. So we'll use this equation, we'll plug that into here, and you could analyze the situation and solve for your terminal velocity if need be, or if you have your terminal velocity, you could solve for things like the density of the fluid, the drag coefficient, etc. Okay, lots of good experimentation. So the very last part to this lab is equilibrium. Doing a DIY equilibrium. And here you get to explore the tension force, etc. So just 1 second. Okay, so in this part of the lab, I used a Jello box, and I'll insert a picture. Very much like your pre-lab. And what you're going to do is you're going to take, like maybe I used a meter stick. And what I did is I tied 2 strings together around the meter stick here. And I connected these 2 pieces of string are connected. So this is 1 full length of string. And then I have another length of string I tied right here. And I tacked to a Jello box. You don't want to use anything stronger than more massive than 1 kilogram, so it doesn't pull too much. So the question is what is the tension T or F of T in all string segments? Okay. So what we want to do is we want to explore, here's theta 1, theta 2, 2 different angles in this arrangement. So we don't want these equal to each other. So theta 1, you don't want equal to theta 2. And we say here we have a tension of the string. Here we have a separate tension that's not equal to this one. Here we have a third tension. And here we have an object held on at rest by this string right here. So if we look at free body diagram, just on this object here, we have weight going down, and we have this T3 going up. And these arrows are equal and opposite because it's an equilibrium. Okay? So on the box, our forces would be the sum of our y forces equals MAY, which is equal to 0. And here, using my convention of positive upwards, positive to the right, I'll have T3 minus mg equals 0. So I have my first equation of motion, and I can use that to solve for T3. Then I can use that to solve for T1 and T2. So the other part here is knowing that T1 plus T2, okay, but what part of T1 and T2 equals T3? So the other part is to analyze what's going on right here at the connection, okay? So this T3, since this is all in equilibrium, this T3 force here is going to be balanced by T1y, the vertical component of tension 1, and the vertical component of the second tension. So now I want to do a free body diagram and the equation of motions on the connection. And on the connection, what I know is that the sum of all my vertical forces in the y direction will equal mass times acceleration in the vertical direction, which here will equal 0. And what comprises of these is T1y component plus T2y component minus T3. And that should all equal 0. And the other thing to note to help you to solve for your 3 tension values is that the sum of all your horizontal forces is also equal to 0. But in this case, what we're going to have is we're going to have the x component of T2 will point in this direction, and the x component of T1 will point in that direction. So what we're going to have is T1x, and go this way, T2x minus T1x equals 0. So the important thing here is to use your components. So how do we do T1x and T1y? Well, we use our angles. So we say T1x is equal to T1 cosine theta 1. Okay? And then T1y will equal T1 sine theta 1. Okay, if you do your algebra and your trig there, that's what you're going to get. And for T2, we're going to have our y component this way, our x component this way. So we can see the adjacent is right along with theta 2. So T2x is equal to T2 cosine theta 2. T2y is equal to T2 sine theta 2. So that gives you the setup for this problem. I hope